Hello, welcome to my class Astrophysics. Today's topic is Photoelectric Effect Part 1. First of all, we have to know some basic fact about the metals and free electrons in metals. In metals, the electrons in the outer shell, called the valence electrons of the atom, are loosely bound. They are quite free to move easily within the metal surface but cannot leave the metal surface. Such loosely bound electrons are called free electrons. That means in metal, a number of electrons which are outermost orbital electrons, they are free, but they are not free to escape from the metal surface. They can move within the metal. And one term related to that escaping from the metal surface, that is the potential barrier. A free electrons in metal can move about freely inside the metal but cannot leave its surface. The moment an electron comes out of a metal surface with its negative charge minus E, the metal acquires an equal positive charge plus E and pulls it back. Therefore, there is thus a potential barrier at the metal surface which the free electrons have to overcome in order to just escape from metal surface. That means metal free electrons, these are negatively charged particles, negative in nature. Just at the moment when it try to leave the surface by leaving same amount of positive charge on the surface, and therefore there is a attractional force between the positive nature of the surface and the free electrons. That means to overcome this, that free electrons have to overcome this attractional force if it emits from the metal surface or try to emit from the metal surface. The minimum amount of work required, minimum amount of energy required by an electron to just escape from metal surface is called the work function of the metal. And in such a case, it is the minimum amount of what is the work function for that particular metal, and that is the minimum amount of energy required by that free electrons to escape from the metal surface. The work function depends on the nature of metal and the condition of its surface. It is generally denoted by W naught or phi naught and measured in electron volt. Now, what is 1 electron volt? 1 electron volt is the kinetic energy gained by an electron when it is accelerated through a potential difference of 1 volt. That means energy gained by the electrons, that is the work done by the electric field, and we know the work done, that is the charge into potential difference. Here the value of the charge, that is charge of electrons, that is equal to 1.602 into 10 to the power minus 19 coulomb into 1 volt. That means when any electrons is accelerated through a potential difference 1 volt, then it gains a kinetic energy, or it get a energy that is equal to the 1.602 into 10 to the power minus 19 joule. Generally in atomic level, subatomic level, electronic level, generally energy transaction taken place in the order of this electron volt. Therefore, openly we are using this unit to measure or to express the required amount of energy or work done. Now there is a concept about we can get a glance of the work function for the different types of metals, work function of some photosensitive metals. Photosensitive means when the light or any other radiations incident on that surface, the electrons emission taken place. And for the cesium, potassium, sodium, all these are alkaline metals. The work function is very less, and that is 2.14 electron volt only. But when we move toward the calcium, that is the 3.2 electron volt, lead, that is the 4.25 electron volt, aluminum, that is the 4.28 electron volt, and similar way the platinum, that is the 5.65 electron volt. Even if copper, silver, nickel, all these have a larger amount of the work function. That means more amount of energy required to escape electron from the metal surface. That means all the metal surface, they have not required same amount of energy to escape from the metal surface. That means number one, the nature of the metal and the condition of the surface. Now work function will be different for the different metal surfaces. Electron emissions. So what is the meaning of the electron emissions? The phenomena of emission of electrons from a metal surface is called electron emission. For the emission of electrons from the metal surface, the energy of electrons must be higher than that of work function of the metal. That means if electrons emitted, or if you want to release electrons from the metal surface, then you have to supply amount of energy, minimum amount of energy to that metal surface, that is known as the work function. Practically all the free electrons in a metal do not have the same energy. That means their thermal or kinetic energy, initial energy, because of the energy distribution of free electrons in a metal, the energy required to eject an electron is different for the different electrons. For the same metal, within the same metal, all the free electrons, they are not moving with the same velocity, and they have not have not possess the same amount of energy, that is the thermal energy. There is a range of energies possessed by the all electrons. An electron with higher energy obviously requires less additional energy to come out of the metal surface than that of lower energy. Work function is the minimum energy required by an electrons to get out of the metal surface. That means work function is not the sufficient energy for the all electrons. It is the minimum amount of energy required for the electrons to emit from the metal surface. And obviously, the electrons already which has higher energy, they require less amount of energy outside of this metal. The required energy for the electron emission from the metal surface can be supplied by the free electrons, supplied to the free electrons by one of the following physical process. Now, how can you supply the energy to the electrons? There are different methods to supply the energy to the free electrons to escape or for the emission of the electrons from the metal surface. First of all, number one, thermo-ionic emission. It is a phenomena of emission of electrons from the metal surface. When heated suitably, the emitted electrons are called the thermal electrons or thermions. And from the name, it is clear if the energy that is coming from the heat energy, that means if we suitably heated the metal surface, and electron emission taken place. That means a required amount of work function it is obtained from the heat energy. That phenomena of emission of electrons is known as the thermo-ionic emissions, and the electrons which are emitted during the process are known as the thermal electrons or thermions. Now, photoelectric emission. It is the phenomenon of the emission of electrons from the surface of metal when radiations of suitable frequency fall on it. That means when radiations means light, photo means radiations, suitable frequency radiation when incident on the metal surface, and if the sufficient amount of energy obtained from the radiations and electron emission taken place from the metal surface, that is known as this type of emission known as the photoelectric emission. Photoelectric emissions, and emitted electrons obviously known as the photoelectrons, just like thermal electrons or thermions. Here the electrons emitted from the metal surface by obtaining energy from the radiations or light, that electrons are known the photoelectrons. Now, another type of field emissions or cold cathode emissions. It is the phenomenon of emissions of electrons from the surface of a metal under the applications of a strong electric field in the order of the 10 to the power 8 volt per meter. And then due to this action of this high electric field, electrons are emitted from the metal surface. And this type of emission is known as the field emissions or cold cathode emissions. It is taken place generally in the lightning conductor when a very highly charged cloud just over the lightning conductor. At that time, electron emission taken place from the lightning conductor. It is due to the effect of the high electric field. This type of emission is known as the field emission or cold cathode emissions. Now, another term is the secondary emissions. It is the phenomenon of emissions of electrons from the surface of metal in large number when fast-moving electrons called primary electrons strike the metal surface. and the electrons so emitted are called secondary electrons. That means when energy required amount of energy uh, for, of electrons obtained from the other electrons, energetic electrons, and emission taken place. This type of emission is known as the secondary emissions, and the fast moving electrons which strike the metal surface are known as the primary electrons, and emitted electrons are known as the secondary electrons. Now, till now we know metal possess free electrons. They are free to move within the metal surface, but they cannot escape from the metal surface. To escape from the metal surface, they require extra amount of energy, minimum amount of energy required, that is the work functions. And if the work function is obtained by the different method, different process, electrons emission taken place. And now our main topics is that is the photoelectric effect or photoelectric emissions. And from the name we can say when the required amount of energy obtained from the light or photo or the radiations, then this emission taken place is known as the photoelectric effect or photoelectric emission. It is a photo phenomenon of emission of electrons from the surface of metals when radiations of suitable frequency fall on them. The emitted electrons are called photoelectrons, and the current so produced is called photoelectric current. And when the emission taken place, and if there is a closed circuit related to that emissions, and we get a current, that current is also known as the photoelectric current. And there was experimental study of photoelectric effect. An extensive study of photoelectric effect was made by Leonard and R.A. Millikan. The experimental arrangement consists of an evacuated glass or quartz tube which encloses a photosensitive plate C, another metal plate A. A quartz window W is sealed on the glass tube, which permits the ultraviolet light or visible light to irritate the plate C. The electrons are emitted by the cathode C and collected by the plate A. And it is the figure diagram. It is one evacuated strong glass tubes. There is a window, quartz window, through which the radiations enter into the evacuated glass tube, and there is a plate, photosensitive plate. This plate is irritated with the help of this incident radiations, and electron emission taken place from this C. And these electrons are collected by the plate A. A plate, it is known as the collector or anode, and C is known as the cathode or emitter of the free electrons. And there is suitable circuit, suitable arrangement, and to obtain the photoelectric current. Now the two electrodes are connected to high tension battery, a DC source, high voltage DC source is known as the high tension battery, a potential divider arrangement, and a micro ammeter mu A, voltmeter V measure the potential difference applied between the two electrodes. When monochromatic radiations of suitable frequency falls on the plate C, the electrons are emitted, which are collected by the plate A. So a current called the photoelectric current flows in the outer circuit, which is measured by the microammeter mu A. That means it is the schematic diagram of the experiment which was performed by Leonard. It is one evacuated glass to you. I am stating again. Just you look at it carefully. See is the photosensitive plate. That means metal which will be treated by some or irritated by some radiations. These radiations coming through the quartz window. It is evacuated one, and normally there will be no any charge carrier because there is no gas or no materials here. It is totally evacuated. There is no charge carrier. It is the collector, and the current we obtained here, that is very less amount. Therefore, we are using here one microammeter, and it is one arrangement. It is a commutator key, and it is a potential divider. With the help of this, we can apply from 0 voltage to certain high DC voltage. And what is the voltage applied between the two plates? One is the C, another A, that is emitter, and the collector. That can be measured with the help of this voltmeter. And this microammeter is used to measure the small amount of electric current which is produced during this process, and it is one commutator key. That means with the help of this arrangement we can change the polarity of the battery which are connected to the plate C and plate A. That means with the help of this we can make the C positive or negative, A plate positive or negative or positive. So this is the total experimentally arrangement. Now there is a source of radiations, and we choose this type of source. With the help of that source we can produce different type of frequencies of monochromatic radiations, and also their intensity can be changed with the help of the suitable arrangement, this type of source here. Now effect of the intensity of light on photoelectric current. Now, what will be the effects of intensity? Intensity means more amount of light in the intensity. And the frequency, if we change the frequency, that means for the visible light, frequency change means color change. And intensity change means the amount of light of the same color that will be more than intensity will be more. There are two parameters regarding the incident radiations. One is the frequency, another is the intensity. Now, first of all, we have to study the effect of the intensity, and when we apply a sufficient amount of potential difference between C and A. Initially, when no light incident on this C, that is photosensitive plate, there will be no current at all, because there is no charge carrier within this evacuated glass tube. And when light incident on it, electrons emission taken place, then electrons, these are moving from C to A under the influence of the electric field. A is connected to the positive terminal of the battery and C the negative. Obviously electrons, they are moving from the negative terminal to positive terminals, and we get a current. The direction of the current obviously opposite to the direction of the electrons motion. Therefore current that is will be always from this to this, from A to C, not electrons. That means if we get any amount of current at any time, that direction of the current always from the A to C, because it is the only source of charge carrier, source of free electrons. And when free electrons emitted from the C, they are only moving from the C to A. Now effect of intensity of light on the photoelectric current. If we allow radiations of a fixed frequency, that means frequency, we choose a frequency, particular frequency, and during this process there will be no change the frequency to fall on the plate P, and the accelerating potential difference between the two electrodes is kept fixed. Then the photoelectric current is found to increase linearly with the intensity of incident radiations. Since the photoelectric current is directly proportional to the number of photoelectrons emitted per second, this implies that the number of photoelectrons emitted per second is proportional to the intensity of incident radiations. That means we take a suitable frequency which is incident on the plate, that is cathode, and the intensity gradually increases, and we keep the potential difference between the C and A, that is the fixed, and that is sufficiently large amount. At that time, it is observed that when intensity of incident radiation is the more, photoelectric current will be more, and the variations of intensity of light, that is, and the photoelectric current, these two are directly proportional. That means more intensity of light, that is more amount of photoelectric current. That means more number of free electrons emitted from the surface. More current means more number of free electrons per second emitted from the surface, and that is directly proportional to the intensity of light when the frequency is constant and the potential difference is also constant. It is first observations, and this observation is known as the effect of intensity on photoelectric current. I am saying again, when for a particular given frequency and a particular potential difference across C and A, when intensity increases, photoelectric current also increases. That means more number of photoelectrons taken emitted when more amount of intensity of that frequency incident on this plate. Now effect of potential. The effect of potential, that means the potential difference between the C and A. and the concept of the saturation current. If we keep the intensity I1 and the frequency of the incident radiation fixed and increases the positive potential called the accelerating potential on plate A gradually, it is found that the photoelectric current increases with the increase in accelerating potential till a stage is reached when the photoelectric current becomes maximum and does not increases further with the increase in the accelerating potential. This maximum value of the photoelectric current is called saturation current. At this stage, all the electrons emitted by the plate are collected by the by plate C are collected by the plate A. That means if we plot the anode potential, the potential difference between the C and A, that is known as the anode potential. For a particular intensity, for a same frequency is constant, intensity for a particular set, and that is I1 is, let us suppose, constant. And when there is no potential difference at that time, also we get some amount of photoelectric current. That means some electrons they are coming from the C to A, when the even if when the potential difference between the plate and the collector, that is constant, and after that if we increase the potential difference, initially the current increases, and after that after a certain value of increase of current, the current remains unchanged, and that is the maximum value of electric current, and that is known as the saturation current. Now if we change the or increase the intensity and then fix it, and again we will perform the same experiment. That means if we increase the anode potential from 0 to certain value, and then gradually current initially increases, and after that again we get a saturation value of the electric current, but the saturation value is more than the previous one if the I2 intensity more than the I1 intensity. Again, if we increase the intensity of incident radiation and fix it, and again we perform the same experiment, anode potential gradually increases. At that time, we get another saturation current, and that I for the another saturation current, that is for the intensity I3. That means we get a saturation current, and that saturation current depends upon the value of that saturation current depends upon the intensity of incident radiations. It is the observation. Maximum the value of the photoelectric current called the saturation current. At this stage, all the electrons emitted by the plate C are collected by the plate. What is the meaning of this? When the incident light is intensity of incident light and the frequency is the same, some electron emission taken place. Initially, when we increase the potential difference, more and more number of electrons which are emitted from the C are collected by the plate A. But after sometimes the number of electrons emitted per second, all these electrons are collected by the collector per second. Then after increasing the potential difference, there is no extra electrons here to collect. Therefore, if we increase more and more potential difference, but the current will be the constant because no extra electrons now present here. All the electrons which are emitted per second are collected by this. And if we increase the intensity of light, then the saturation current will be increased, but there will be also another saturation current. And again, further, if we increase the intensity, more amount of saturation current we obtain. That means it is now clear the number of electrons, emitted electrons, that basically depends upon the intensity of light. Now, our next observations. Cutoff potential or stopping potential and maximum kinetic energy of the photoelectrons. And here we observe, even if when we are not applying any potential difference, we get a electric current. And how the experiment is performed. Now when this jockey, if we move the jockey from left to right, then potential difference increases, applied potential increases. But when the jockey is placed here, the circuit is closed now, but potential difference applied here 0. The circuit closed, that means the current can pass through it in this way, but the potential difference is 0. Even if when there is no potential difference, at that time also we get some amount of current. Why we get some amount of current? And now it is questionable. Now if we supply a negative potential, and if we stop the some amount of electric currents, there it is obtained due to the electrons which they are coming by themselves without any help of the potential difference between the C and A. and if we want to stop them again, the flow of electrons or coming from electrons from the C to A, then we have to apply some negative potential, because we know electrons are negatively charged particles, and if we apply the negative potential at the end A, that means at the collector, the electrons will be there will be repulsive force between the electrons, and therefore electrons will be gradually stopped. Now if we apply negative potential on plate A with respect to the plate C and increase its magnitude gradually, it is seen that the photoelectric current decreases rapidly until it becomes zero for a certain value of negative potential on plate A. That means when we increase the negative potential by changing here with the help of this commutator key, now this terminal connected to the positive terminal of the battery and negative terminal of the battery connected to the plate A, and we are starting from the zero potential. And when we increase the negative potential gradually, it is observed that current, photoelectric current gradually decreases, and after a certain value, at a particular value of the negative voltage, the current will be zero. This voltage is known as the stopping potential. Now if we apply negative potential on plate A with respect to plate C and increase its magnitude gradually, it is seen that the photoelectric current decreases rapidly until it becomes zero for a certain value of negative potential on plate A. The value of the retarding potential, that is negative potential, at which the photoelectric current becomes zero, is called cutoff or stopping potential for the given frequency of the incident radiations. That means this retarding potential, that is negative potential, at which photoelectric current becomes zero, is called cutoff potential or stopping potential for the given frequency of the incident radiations. Here we are saying for the given frequency. That means it is observed for the different frequency, this cutoff potential will be different. For a given frequency of incident radiations, photoelectrons are emitted with all velocities ranging from 0 to a certain maximum value, V max, at the stopping potential V naught. When no photo current is obtained, the work done by stopping potential on the fastest electron must be equal to its kinetic energy. That means this stopping potential is required to stop maximum kinetic energetic electrons, and that stopping potential therefore related to the V max. That means in this case we can easily write kinetic max, maximum kinetic energetic of electron, the energy of kinetic energy of maximum energetic electrons, that is half into m into V max square, that is equal to charge into stopping potential, that is charge of the electron in the E into V naught, where E and V max are the mass, m is the mass of electrons, E is the charge of electrons, and V max is the maximum velocity of electrons. That means the electrons which are emitted from the metal surface, they have a range from 0 to maximum value, which electrons at maximum value, and they can move themselves even when there is no potential difference is applied between the C and A, and due to their initial large amount of kinetic energy. And to stop them, we have to apply negative potential, and at which negative potential they are completely stopped. And how can we understand at that negative potential there is no current? That means all electrons are stopped, and practically this negative potential always related to the maximum energetic electrons. This stopping potential is not related to any emitted electrons. These are related to only maximum energetic electrons. If we repeat the experiment with the incident radiations of the same frequency, but of higher intensity I2, I3, that is I2 greater than I3 greater than I2 and I1, we find that the values of saturation current have increased in the proportion to the intensity of the incident radiations, while the stopping potential is still the same. That means if we increase the intensity, we will observe the saturation current, that means number of photoelectrons will be more. That means photoelectric currents mainly depends upon the intensity, that is number of electrons emitted per second, that depends upon the intensity, but not the stopping potential for all cases will be same because frequency is the same. That means the stopping potential is related to the frequency, but maximum saturation current is related to the intensity of incident radiations. Thus, for a given frequency of incident radiations, the stopping potential is independent of its intensity. This in turn implies that the maximum kinetic energy of photoelectrons is independent of intensity of incident radiations. That means there are now two terms: maximum energetic electrons, and another is the maximum number of electrons emitted per second. The maximum number of electrons emitted per second, that depends upon the intensity, but maximum energy of the electrons, that depends upon the frequency only, not depends upon the intensity. More intensity, but in all cases the stopping potential same. That means the kinetic energy, maximum kinetic energy of the electrons remains unchanged even if intensity increases. Number 3, effect of frequency of incident radiations on stopping potential. Now, if we use the different frequencies to study the effect of frequency on photoelectric effect, the intensity of incident radiations at each frequency is adjusted in such a way that the saturation current is same each time when the plate A is at a positive potential. The potential on the plate A is gradually reduces to 0, and then the increase in the negative directions till stopping potential is reached. The experiment is repeated with radiations of different frequencies. That means now we are taking different frequencies and we adjusted different light. That means different frequency means different color of light, maybe the different source of light, in such a way, and there in all cases saturation current is the same. Saturation current is the same in all cases. In this way they are adjusted, but the frequency are different. That means saturation current same means the number of photoelectrons, maximum photoelectrons emitted per second, that will be same. But when we decrease the potential between these, gradually photoelectric current decreases, and after that when we apply the negative potentials, it was observed that for the lower frequency the stopping potential negative value is the less, and for higher that is negative value is the more, and higher that is the negative value is the more. In this case nu3 greater than nu2 greater than nu1. That means for the lowest frequency the value of the numerical value of the stopping potential is the less, and for the highest frequency the numerical value of the stopping potential is the more. That means the stopping potential clearly depends upon the frequency, and mainly depends upon the frequency. The variation of the photoelectric current with the anode potential for different frequencies of incident radiations. It is observed that the value of stopping potential increases with the frequency of incident radiations. For frequency nu3 greater than nu2 greater than nu1, the corresponding stopping potentials vary in the order of nu VO3, that means stopping potential for the third greater than VO2 greater than VO1. This implies that greater the frequency of the incident radiations, greater is the maximum kinetic energy of photoelectrons, and hence greater is the retarding potential required to stop such electrons completely. If we plot a graph between the frequency of incident radiations and the corresponding stopping potentials, if we plot this, it is the frequency and stopping potential for the different metals. Let us suppose there are two metals, metal A and metal B, and we are plotting the stopping potential. It is observed at a particular frequency the stopping potential becomes 0, and that means practically below at that frequency there is no, or below that frequency there is no emission of electron taken place, and above that frequency for metal A the stopping potential proportionally increases. That means stopping potential is directly proportional to the frequency. And for the metal B, that is these two are parallel graphs, straight line graphs also, but their initial frequency That is the nu not dashed. It is more than this metal A in this figure diagram, and that means it is a linear variations of stopping potential with frequency. And we observe below a particular frequency no photoelectron emission taken place, and these are not same for the metal A and metal B. Variation of the stopping potential with frequency of incident radiations, this type of graph we obtain, and all these are obtained from experiments. That means all these are experimental observations. Till now we are saying all these observations coming from the experiment. Why? So we observe till not now known to us. We are observing. This is a fact, experimental fact, that for the metal A, the variations of the stopping potential with frequency, this type of graph. For metal B, this type of graph. These graphs reveal the following facts. What are the facts related to this graph? The stopping potential increases linearly with the frequency nu of the incident radiations for a given metal. Number one. That means linear variations. Stopping potential increases linearly with the frequency of the incident radiation. Frequency means frequency of the radiations which incident on that particular metal surface. There exists a certain minimum cutoff frequency. It is not the cutoff frequency. Cutoff frequency means below that frequency there will be no photoelectric emission taken place. There exists a certain minimum cutoff frequency for which stopping potential is zero. This minimum value of frequency of incident radiations below which the photoelectric emission stops altogether is called threshold frequency. The minimum value of the frequency of incident radiations below which the photoelectric emission stops altogether is called threshold frequency. That means it is the minimum frequency required for the photoelectric emission, and above that frequency photoelectric emission always taken place. Below that frequency there will be no emission of the electrons from the metal surface, and this threshold frequency is not the same for all metals. It will be different for the different metals. For the two different metals A and B, these graphs are parallel straight lines. That is, they have same slope, but the threshold frequencies are different. Threshold frequency means from which frequency the emission taken place. But the threshold frequencies are different for the two metals, but their slopes are same. Variations, similar variations. Above the observations, the above observations imply two important facts. Number one, the maximum kinetic energy of the photoelectrons increases linearly with the frequency of the incident radiations, but is independent of its intensity. Maximum kinetic energy, why we are saying that? Stopping potential is directly related to the maximum kinetic energy. More kinetic energy, more amount of stopping potential. Therefore, from the above fact, we can say the maximum kinetic energy of photoelectrons increases linearly with the frequency of incident radiations, but independent of its intensity. If we increase the intensity, if we more and more intense light is incident, but frequency is the same, there will be no effect on the stopping potential. That means the maximum kinetic energy not depends upon the intensity. More and more intensity, but kinetic energy maximum that remains unchanged. That only depends on the frequency. Number two, for a frequency nu of the incident radiations less than the threshold frequency, no photoelectric emission is possible. Howsoever large the intensity of incident radiations, if you increase intensity more amount of light, but it was observed that there will be no emission taken place if the frequency of incident radiation more less than this threshold frequency. The time interval between the incident radiations and that is the obviously incident radiations, when radiations is more than the threshold frequency for that particular metal, the emission of electrons is of the order of the 10 to the power minus 9 second. That is, photoelectric emission starts instantaneously. There is no time lag between the incidence on the photons, incidence on the light radiations on the metal surface and the emission of electrons. These are the different observations we observe experimentally. Practically, this experiment was initially performed by the Leonard and the is Millikan, and they observed observed different variations of the photoelectric current with the potential difference across C and A, and the variations with the intensity of the variation with the frequency, and they observe these facts. Now in this first part, it is end of the first part, and in our second part of the photoelectric emission, photoelectric effect, we will discuss what are the causes behind this. Now we stop here.